sideways and we start from the bottom, move up, am I hitting the graph down here? Well, it's hard. You could argue maybe that you are. This right here actually continues like this and flattens out and never actually touches the x-axis. We call this a horizontal asymptote. We'll talk about that more later. But I'm telling you that this graph never goes below the x-axis. I'm just clarifying that for you, okay? So, do I ever have any y values down here? No? Okay. How about here? How about 0? Does this graph ever give me a y value of 0? No. How about a little bit above 0? Yes, right? And remember we talked about there's no number right next to a number? So the only way for me to tell you that this starts at 0 and goes how far up? Forever, because these y, I'm going to get y values like that forever. So how do I say from 0 to forever but not including 0? I'll do parenthesis 0 to infinity. Remember, domain is always x values, range is always y values, right? Any questions there? Do I have any x-intercepts? Does this graph ever hit the x-axis? No, right? So we just put none. All right. How about y-intercepts? Yes, I have one y-intercept right here. Now, you can either tell me the y value where it hits, or you can give it to me as an ordered pair, like a point. I suggest the point. So what is that as a point, as an ordered pair? 0, 1, right? The x-coordinate is 0. The y-coordinate is 1. Any questions there? No? Okay, now this tricky part for symmetry. When it comes to symmetry, we are going to look at 3 types of symmetry, all right? The first type of symmetry is when I draw this graph, is it a reflection of itself over the x-axis? So if I took this blue graph and reflected it over, does it land on top of itself? No, there is no graph down here, right? So I do not have reflection over the x-axis. If I take this graph and reflect it over the y-axis, does it land on itself? Yes. So if I took this part right here and flipped it over, it would do this, wouldn't it? And if I took this part right here and flipped it over, it would do this. Do you all agree that that's the reflection over the y-axis? Did that just land right on top of itself? No. 1 point did. 1 point didn't move, but the rest of the graph didn't land on itself. So if we reflect it over the x-axis, it definitely is not landing right on top of itself. If we reflect it over the y-axis, it's not landing on itself, right? So no symmetry so far. Now the last one is what we call symmetry with respect to the origin. And it always confuses students what symmetry with respect to the origin is. There's three symmetries we're looking at. Reflection over x, reflection over y. The last one is symmetric to the origin. And what that is it's a double reflection. It's both the reflections we just talked about, one followed by the other. So if I reflect this over the y-axis, I would get this, wouldn't I? Do y'all see that mirror image? And now reflect that over the x, and you would get this. Do y'all see it? It's a double reflection. That's called reflection over the origin. When I do that double reflection, am I landing back on top of myself? No. So this is probably a bad example to start with because we have no symmetry at all. There's none. Pardon me?
13 fits all of them.
We can go back and look at 13. Yeah. So we would say none here, or just no symmetry. All right, no symmetry. Do you want to look at 13? We can look at 13. Let me move it up a little bit. There we go. We can do 13. Okay, for 13, start from the beginning. Look at the arrows. All right, domain. As I move from left to right, am I hitting the graph over here? Yes, because this goes like this and that goes like that. So I'll be hitting over here, right? How far this way will I be hitting? Forever, right? Forever. And I keep hitting until I get to where? Oh, right there, right? Right here, I stop hitting the graph. That's the last point And then there's like this abyss, right, where there's nothing, I don't have any graph, right? And then it picks up again right here and continues, and then I start hitting again. You'll see that? So how do I say that? It's everything to the left forever here and everything to the right forever here. Can you tell what number that is? -1. So everything to the left of -1, negative infinity, comma, -1, parenthesis, right? Oh, parenthesis or bracket? Hold on. Bracket, because I actually do have graph at -1. Union, and now from 1 forever. And I do have graph at 1, so 1 to infinity. Y'all understand that domain? Anyone need clarification? What about range? Yeah, do I have graph down here? Am I hitting? Well, these two arrows go down forever, right? So I'm going to have y values down here. Do I ever have any gaps or anything? No, all the way up forever, right? So negative infinity to infinity. Do I have any x-intercepts?
Yes.
Yes, where? -1 and 1, right? That's where I hit the x-axis. So let's write these as points. -1, 0 is the first one, and 1, 0, right? -1, 0 is this point, and 1, 0 is that point. How about y-intercepts? Do I ever hit the y-axis? No, so I have none, right? Now the symmetry. If I were to take this graph and reflect it over the x-axis, that means everything that's up here comes down, everything that's down goes up. Does it land right on top of itself? Yes. So I have symmetry over the x-axis. So I have x-axis symmetry, right? How about y-axis? If I take this and reflect it over here, and I take that and reflect it over there, does it land right on top of itself? Yes, right? So that's y-axis symmetry as well. And now the hard one. This is the one that's kind of hard to see. So let's just ignore this side for now, okay? If I were to take this and do a double reflection, so reflect over the y first, and then reflect over the x. Do you see what it would be? And then do the same thing for this one. Reflect it over the x and then reflect it over the y. Does everything land right on top of itself? Yes. So if double reflections give you the same function, then you have what you call symmetry with respect to the origin. That's what you were saying, right? 13 is everything. All right, let's look at another one. How about...
I have a question.
Yes.
So on the test, would we have to write all the symmetries out? Or?
Yes.
Okay.
If it had multiple symmetries, you would say which ones it had. Let me do. How about 17? Domain. Well, this graph only exists, what, from 0 to the left, right? For x values. So I would say negative infinity to 0, bracket or parenthesis? Bracket. Range. All real numbers, because this goes down, it keeps going down forever. This goes up and goes up forever. So if we start drawing horizontal lines, we will have graph the whole way. Do I have any x-intercepts? Right there, right? That's the point 0, 0. Do I have any y-intercepts? Same point, right? That same point that hits the x-axis is the one that hits the y. So you could have your x and y-intercept be the same point. If it's the origin, that'll be the case. All right, symmetry. If I reflect that over the x-axis, is it the same function? Yes. So x-axis, yes. How about y-axis? If I reflect this over the y-axis, it's not the same thing, is it? So no. And then over the origin?
Yes.
So imagine, for origin, you have to do the double reflection. So first, let's reflect over the x. It's itself, right? But now go over the y. You don't get it, right? It doesn't wind up being the same thing. So you don't have over the origin here. I'm going to draw one real quick for you, just so you can see another one that does have origin symmetry. Here's one. That has symmetry over the origin. Can you convince yourself that it does? I'll try and help you convince yourself. First, I'm only going to look at this part first. If I reflect that over the x, I get this. Right? Do you all see that's reflected over the x? Now reflect that over the y, and do you see that if you do that, it'll land right on top of itself? That's an example of origin symmetry. Okay? Is this origin, do you have x-axis symmetry here? If I just flip it this way, is it the same graph? No. How about y-axis symmetry? If I flip it this way, is it the same graph? No. But if I do a double flip, it does, right? And that's origin. So that would be origin only. Okay. Let me zoom out here. I want to do one more that has kind of an interesting little thing happening here. Let's do 19. 19 is a good one. What I like about 19 is that open hole that it has. Do you see that open hole right here? Okay, let's talk about the domain first. Does it go to the left forever? No, right? I don't have anything over here, do I? Nothing over here. Not until I get to where? 0. Now, does my graph actually, is it defined at 0? If I plug 0 in, does it look like my graph is defined? No. So it's what we call a vertical asymptote. But it's getting closer and closer to this y-axis. So as soon as I get past 0, I'm going to have graph down there. So how do I say that? Parentheses 0, right? So from to the right of 0, I have graph, and then where does it stop? At 3. Does it actually have a value at 3? So if you plug 3 in, you have an open circle, right? Now, I don't know why they put a 2 here. This actually contradicts itself, because you can't tell me that it's defined to be 2 if you have an open circle here. So this is actually an error in the book, I believe. They either need to make that solid to make it match, or they need to get rid of that and just say that it doesn't exist. So let's just act like that's not there.
You're just telling you the open hole isn't that coordinate.
Yeah, but that implies that when you plug in 3, you get 2, right? That's the idea of an ordered pair. It tells you the input and output of the functions. So that implies that there's an output. So if we assume there's no output there, then the domain would go from 0 to what? 3, but not including 3 because there's an open circle there. How about the range? So do I have function down here? All the way down, right? So from negative infinity to, where do I stop? At 2. Do I ever reach 2? No. So I put a parenthesis on the 2. If this was a solid dot, then I would put a bracket on that 2. If this was a solid dot, I would have put a bracket on the 3. But because it's open, I have to use parentheses. Any x-intercepts? Just one, right? Right here? So that happens at, what? X value of 1, y value is 0. Right? Do I ever hit the x-axis? I'm sorry, y-axis. No, so I have no y-intercepts. All right, symmetry. Let's try x-axis symmetry. If I flip this over the x-axis, is it itself? No. How about the y-axis? No. How about a double reflection? Here, let's see, that's y-axis symmetry. Right, that's y-axis reflection. then reflect over the x. No, there's no graph over there, right? So this has no symmetry at all. Okay, I hope that that helps kind of like get through this first concept here of this section, which is just if we give you a graph, can you identify the values, intercepts, domain, range, symmetry? Let's see what else we got here. Okay, let's look at this number 26, and I think what I'll do is I'll put this Can you all see that all right? Over there on that TV right here? Okay. So I'm going to give myself a blank screen here. This is a new problem. What we're given here is a function. So this is number 26. We're given a function f of x equals negative 3x squared. How do I know this is a function? Because I wrote the notation, right? F of x. So I've given you this function, right? This is given. And the first part, part A, says, is negative 1, 2 on the graph of that function? Yeah, so what we want to do, this negative 1, 2 being on the graph means that when you plug what into the function? Negative 1, you should get 2, right? And that's the question. Does that happen? Right? To say, is this point on that graph means that when I plug negative 1 in for x, does it spit out 2? So let's plug negative 1 into this. So I'm looking right here. Plugging in negative 1, negative 3 times negative 1 squared plus 5 times negative 1. See, that's what happens when you plug negative 1 into the function. We're asking ourselves, is that equal to 2? Is it? What's negative 1 squared? 1 times negative 3. Negative 3. And then 5 times negative 1. Negative 5. Is that equal to 2? No. That's negative 8. That doesn't equal 2. So is this point on the graph? No. That point is not on the graph. So, no. All right, part B says, if x is negative 2, what is f of x? So what are they saying to do here? Plug negative 2 into the function, right? That's it. So we're going to find f of negative 2. That means you plug negative 2 into this. Negative 3 times negative 2 squared plus 5 times negative 2. And just remember this right here, you square the negative first, right? Negative times negative is positive. So negative 3 times 4. And then this you multiply, that'll give you negative 10. This is negative 12, take away 10, negative 22. Right, this is just arithmetic. Y'all understand all that? So this means what it's asking us, what can we conclude is the point that corresponds to this on the graph? Well, when we plug in negative 2, we get negative 22. That's the point that's on the graph, right? We know that that point's on the graph. What's the difference between that question and part C? Yeah, instead of plugging negative 2 in, they're asking when is the function negative 2, right? They're saying when does the function spit out negative 2? And so what we need to do is we need to set the function equal to negative 2. And when I say set the function, that means we need to set negative 3x squared plus 5x equal to negative 2, and then solve that equation, right? We have to solve that equation. What kind of equation is that? It's a quadratic equation. Do we know how to solve quadratic equations? Yes, we should, right? So this problem is saying, hey, just if x is negative 2, what's the function's value? Okay, what point corresponds to that? Good. This is saying, hey, if the function is equal to negative 2, what x value makes that happen? We might have two answers, right? How do I know I might have two answers? It's a quadratic, and quadratics can have how many answers? 2, 1, or none, right? So we might have none. Let's just see. Okay, if you had to solve that, how would you all solve that?
Move the 2 over the left.
You'd move the 2 to the left, okay, and then what? AC method, what's your other option? Guess and check, quadratic formula, right? You have basically like 3 things on the plate here for you. Now, okay, I'll move the 2 over because that's what was suggested. I'm going to add 2 to both sides. But I really do not like working with negatives in front of my x term. I do not like that. So what I'm going to do is I'm going to multiply the left and right-hand sides by negative 1. Can I do that? Am I allowed to do that? Multiply both sides of an equation by a number? Negative 1 here, negative 1 here. If I do that, what's the effect of multiplying this by negative 1? It becomes, just changes the signs, right? And 0 times negative 1 is still 0. In other words, you're allowed to just change the signs of everything. I just like that a little better. I'm going to try my AC method here. 3 times negative 2. Yes?
Never mind.
Sure?
I messed up, yeah.
Okay. So I'm doing 3 times negative 2 gives me negative 6. I've got the negative 5 in front. I'm trying to come with 2 numbers that do this. Negative 6 and positive 1, right? And then I break this down. I put x minus 6, x plus 1, but then the very important step, you have to take the 3 here, divide 3 here, divide 3 here, reduce the fraction, right? We've been through this. This becomes a 2, x minus 2. This one doesn't reduce, so I swing the 3 back out front. I get 2 answers there, right? You set each of these equal to 0. I'm just going to write the 2 answers. So x is 2. What's my other one? Negative 1/3. So if you set each of those to 0, you get two solutions. All right, so the question was, if f of x is negative 2, what is x? And what point or points are on the graph of this function? So I know that when I plug in 2, what does it spit out? Negative 2, right? That's where I got this from. And I also know that when I plug in negative 1/3 for x, it spits out negative 2 as well, right? So there are 2 points on that graph that correspond to that y value of negative 2. All right, I'm working on part D here. What is the domain of this function? So the original function was negative 3x squared plus 5x, right? That was the original function? What's the domain of this? So this goes back to last class. If you're given a function and you're asked for the domain, yes? All real numbers. Why? There's no division by 0, there's no fractions in here, and there's no roots, no even roots, right? So if we don't have any fractions, we don't have any even roots, the domain of this would be all real numbers, negative infinity to infinity. All right, that answers part D. Part E, list the x-intercepts of the graph. Okay, this is part D. E. Find the x-intercepts. Okay. How do we find the x-intercepts of this graph? So yeah, anytime our graph hits the x-axis, right? Anytime the graph hits the x-axis, what can you tell me about the y-coordinate? It's 0, isn't it? So to find the x-intercepts of any function ever, what you do is you take the function and you set it equal to 0. Have we done that yet on this problem? No, we set it equal to what earlier? -2, but not 0, right? So we've got to do this now, which is going to be another quadratic, isn't it? -3x squared plus 5x equals 0. There are different ways to solve this, but the easiest way is to not do AC method and to not do quadratic formula because there's only 2 terms on the left. And they both have a GCF, right? What's the greatest common factor? X. Pull an x out, it will leave you with -3x plus 5 equals 0, right? If we pull that GCF out, and GCF is always the first step for factoring, right? When it comes to factoring, GCF is always the first thing we do. So pull out the GCF, and now because it's multiplied, we can set each of those equal to 0. And see, we don't need any special methods. It's just, we should be right there here at this next step. We set the first one equal to 0. We set the second one equal to 0. And now this one, we already have an answer, right? 0, 0. 0. Over here, we'd have to move things around, right? Add or subtract 5 on both sides, divide by -3, and 2 negatives divided together would be positive. Okay, I boxed those, but I actually want my final answer to be points. So if this is the x-intercept, that means when I plug in 0, it spits out 0. And when I plug in 5/3, it spits out 0. Those are my 2 x-intercepts. Last part, part F. List the y-intercepts. Y-intercept, if there is one. It says if there is one. F, y-intercept. Okay, so when you talk about a y-intercept, that means where you hit the y-axis, right? What can you tell me about any y-intercept? The x-coordinate must be what? 0, because you're on the y-axis. And then this, we don't know what it is, right? So in order to find the y-intercept, you don't set the function equal to 0. What do? You plug 0 into the function, right? You plug 0 into the function, not setting the function to 0. That's how you find the x-intercepts. To find the y-intercept, you just plug 0 into the function. And that's usually easy for students to do, right? F of 0 is, in this case, well, if you plug 0 in here, everything goes away. You just get 0, don't you? Just kills everything off. So this, when you plug in 0, you get 0. That's my y-intercept as well.
We already got one of those with the next.
We actually saw, we could have seen it here, right? Okay. All right, we are going to move on. That concludes 3.2, all right, which was very visual, right? There's a lot of visual stuff here. We're going to move into 3.3 now. What's going on? Are y'all all right? I just have this really eerie feeling right now. Like I feel like I've lost, like that quiz just completely derailed everybody in here. Everyone's like freaking out or. All right. All right, 3.3. All right, this I have some more like formal notes for this, all right? That's why I'm projecting today, because we have a lot of things to look at that we don't want to write down. Remember, this is all in the ebook, so we're not going to, I don't want you sitting here copying all these definitions down, right? What we're going to do is I'm going to go through some definitions, and then we're going to do an example. And then definitions, then an example. Definitions, example. All right, so we are talking in 3.3 about properties of functions. The first property we want to talk about is this property of a function being even. All right? So if you were to look at all the functions out there and you just grab a function, you could ask, hey, is that an even function? Well, you'd have to be able to answer this question. Is this equal to this? Is this equal to this? That's what it takes for a function to be even. So let me try and explain this to you visually, what it means to be even. So to be even means that when you plug in negative x into the function, it's the same as plugging in positive x. Right? If I plug a negative value into the function, I get the exact same thing as when I plug in a positive value. Let's see if we can't visualize that. So let's just say that when I plug in, let's pick a negative number. Let's just say when I plug in -2, I'm just making this up. When I plug in -2, let's say it spits out 3. Okay? To be even means that when I plug in -2, I get the same thing as plugging in +2. So what should I get if I plug in +2? 3 as well, right? That's what it would mean to be even, that when I plug in the negative value, I get some answer. It's the same as plugging in the positive. I get the same answer. See that? And that should work for every value I ever pick. So let's say I had another value here at -3. Let's say it was 1. Then what should it be at +3? 1. What about at 0 if I tell you that the answer is 1? Well, f of 0 would be the same as, 0 is not positive or negative, right? So they should be the same, so that should be it. Do y'all see what this picture would look like? Like if we pick another point, let's say I put it here, on the other side it would have to be the same? Do y'all see what kind of symmetry we have here? It's over the y-axis. Do y'all see that? Now I could connect, let's say I connect all these together and I say it looks like this. This graph would have to look the same way. You see? So even functions, all even functions have to satisfy this, and they give us y-axis symmetry. Now, why do they call it even? Well, that's a question that can be answered in Calculus 2. In Cal 2, we get to a point where I can finally say to you why we call it even. But for now, you're just going to have to accept it, even. We're okay? All right, that's the first property. Now let's talk about odd. Okay, what does it mean for a function to be odd? Well, the notes, I can bring the note up, but here's